Hello and welcome back to a new video in my C++ tutorial series. In today's video, we're gonna talk about linked list. That's right, we're gonna get to a new concept that we haven't talked before. I think I have teasered it in like one of the INI, I think in the INI parser where we have written like this INIX.c, which has done like a lot of madness of storing INI data into some structure. I think we already used the linked list here. Yeah, we already used this here by having like a first KV and the next KV. So you should be already familiar with the general concept. However, what we want to do today is we want to explore this a bit further. So what we're going to do today is we're going to extend our cats and dogs example by providing a linked list that can store animals so that we can, for example, age them all together and, yeah, do many things with them. So in general, the idea is to manage cats and dogs inside of some structure. Now, if you would want to manage cats and dogs straightforward, you would want to write an array, right? If you would want to manage many cats, you could try to make like a cat array and call it cats and put 50 cats in here. However, this would not work because the cats cannot be default constructed. So what you would need to do is say maybe like 2 cats and directly provide an initialization to that array, and this actually doesn't even work. That's interesting. Why don't you work? Think you would need to provide like the actual name or actually call the constructor manually because we can't convert it. But what you can do is you can kind of like create a cat array like that and manage multiple cats in it. However, what would not work is do it a bit different. You could like say like, all right, this is like a dummy cat and this is another dummy cat, and later on you could say something like cats at 0 is std move of a new cat constructed by the name of Bob, for example, and you would be able to overwrite that cat at slot 0. But then to actually know how many cats are in here, you would need an integer and I equals 0, which basically indicates how many cats there are. And if you do this, you increment this, and then you create another cat, for example, like on slot 2, and maybe call it Eve, and now you want to clear the cats at the slot 0. So if you want to clear a cat, you would need to std move a dummy cat in here again, and then you would need to decrement I, but if you would have now decremented I, it seems like you just removed Eve, and yeah, as you can see, like managing cats inside of arrays, it's not a good idea, right? It's not a good idea, it's hard, it's not how we want it. So what we really want to do is we want to manage cats in some certain data structure. Now, by default, the standard library does already provide data structures, which we could use. So, for example, what the standard library would provide is a so-called vector, a std vector. And what you could do is you could create an std vector of cats, call this one cats, and then what you could do is you could like go in here and you could push back. It's called pushback. It's like pushing back a cat. Now of course it's a cat and not a dog, but what you can do is you could like push back them in. You can actually erase them by saying erase, and what you would then want to erase here, you need to find a cat, and if you would want to find a cat, it's gonna be a bit more tedious because you would need to call something like std find, and then you would do something like cats begin, and you would do something like cats end, and then you would need to search for a cat, which in this case wouldn't work because I think we don't have implemented finding cats, comparing cats to each other, and it really wouldn't work, right? You can see like the syntax looks good, but in reality, if I would build this, it's probably gonna fail, I assume. Yeah, binary operator, no operator found, which takes the left-hand operator of type cat. So it tried to find a cat because it's kind of like comparing them and then breaking out of a loop. And this is like where it tries to find them and it doesn't work. But really, as you can see, even through this isn't working here, you can see that you wouldn't even understand it, right? This is like very complicated. A vector, a cat, pushback, why pushback? Why is it called arrays? Why do we need to do std find? What is that begin and end of cats, and how does that all comes together? So really, It's a madness. It doesn't work like it should. Right? We don't want to do it like that. We don't want to do it like that because we don't understand it. And that's the problem with many tutorials. With many tutorials in C++ that don't really explain what's happening here. Because, well, they just put you that code on and they say, right, that's it. This is how you do it. But you can't understand what's going on here. And to understand how this is going on, you need to write your own like vector class. It's important that you write your own container, at least one container in your life. You need to at least write one and understand one container and understand how they work, how this begin and end work, and how the concept of pushback and things like that work. And that's important. You need to understand the basics around behind these containers and how they work and how they get together. And this is why this video is there. This is to explain you how to create containers by writing a linked list. Now, how does a linked list work? Well, a linked list kind of like works like an array. It is a dynamic array, and a dynamic array of a certain number of elements. This is a linked list. And in general, how this works, if I would have like my linked list L, I'm just going to call this L, and the general idea here is that L kind of like points to a, for example, in this case, cat. It points to a cat. The cat again points to the next cat, and at some point they're gonna kind of like point to null pointer or have a null pointer, which basically means that there's no more cat left. If you want now insert a new cat would be allocated dynamically on the heap, and this null pointer would be replaced by a new cat, which again would point to a null pointer, so that the chain is kind of like completed. So the idea is, instead of having a big pre-allocated array, you're just gonna allocate one element at a time, and this one allocate that one element that you are gonna allocate, this one single element just gets allocated, gets the data which it needs to get, and it points to null pointer. So you generally have like one cat, one cat, one cat. So in case of 3 elements, you would have 3 allocations. The nice thing is that all of these elements are independent. So if you want to delete that one single cat in the middle, you can do this. You can delete it out of there and just need to adjust the pointer so that everything is good. This is the concept of a linked list. But we're going to see this in a second when it all comes together, and we're going to do it. Now, I'm going to add a new item here. Let's create a header, HPP. Let's go in here, header file, HPP, and let's call this one linked list.hpp. Now I'm going to start directly implementing this actually for a pet pointer. So what I'm going to include is I'm going to actually include pet.hpp, and the linked list is going to store pet pointers, but later on we're going to transform this one to a template so that we can do it a bit better. How did I call the namespace? Pet manager, I think. Yeah. However, this is actually not a pet manager. Let me actually write this class directly in there, and let's just call it linked list to just have it in here. It's not really dependent on the pet manager. The linked list is kind of like global, even though I told you that global namespaces are not good and it should go into something like std, or in my case maybe something like fuselutil. This would be a good name because nobody would call this like that. So let's call this fuselutil. You could also call this futil. But as more concrete you are in these namespaces, the less important, or the less is the chance of having collisions with other people. So if I would include this, I would just use the namespace fuselutil here again. All right. So now we have the class of a linked list. Now, this class is going to contain some public stuff, some private stuff, and in general what we want to do, the first element that it's going to manage is like a pet pointer, or a pet manager pet pointer, right? This is like the first element, like m first would be the first pet, which is by default null because a list is by default empty, right? You have a list, it's created, it's empty, and then you add elements to it. However, there is one important or one big issue if you would directly point to a pet. Well, the issue is that you can't really point forward because a pet does not have a next pointer, and it's not meant to actually change the class pet and add a next pointer so that you can chain them together, because a pet doesn't support chaining. The pet might have a pointer or a reference to a pet which is its mother or its father or something like that, but the idea is not that you chain pets together to kind of like manage them, next pet or something like that. That's not the idea. The idea is that you're gonna have an acceleration structure, or like a management structure, however you want to call that is kind of like defining the content, which is like the pet, and the link to the next pet. So what you want to do is you want to create your own struct. I always tend to put them inside of the class. So the linked list is the class here. They are our public functions and private members. And up here, we're going to have a struct. which I'm going to call element. So inside of that linked list, I now have a struct called element, which actually allows me to access this like that. So linked list element is kind of like the way to access the element. However, I could not access it here because it's private, and since it's private, I cannot access it outside of the class, and that's the exact idea. You don't want to access the element from outside of it. The idea is that the element is stored in here, and what you want to do is you want to actually refer to that element and call this one first. So instead of directly pointing to the pet, you are pointing to the first element. Now what the element does, it actually points now to the pet, so the pet manager, pet pointer. I'm gonna call this one just storage on a struct because everything is public. I didn't put the m underscore in here. So what it does, it basically just points to the storage of its internal data, and that storage would be by default like null pointer. However, I'm not gonna set this to null pointer here. So what I'm gonna do in general, I'm just gonna leave this one empty because this one is handled later. What I want to as well add, of course, is I want to add a pointer to the next one. So an element pointer next, that one can be easily set to null pointer. Now this struct shall get a few constructors. First of all, I do not want to have the default constructor. That one will be deleted because it's no longer required. We don't never need the default constructor. We always gonna have a pet manager pointer that we're gonna get. Pet manager pointer is always where we constructed this, and we're gonna call this one element, or just want to call this one data, and inside of that storage we're gonna store the data. That's how we do it. By default, we just construct it with a pointer to it, store it in the storage, and everything is good. This is like all handled on construction of an element. That's the whole idea. Now you have like the next one, this is automatically initialized, and the pointer to the actual storage element. And you have the first element in the chain. Now let's actually implement how it works to actually add an element to the list, and this is where the nice names like pushback come into place, because pushback is in general like the name to push it to the pack. But I personally like to call this differently. I like to keep my conventions and call this one append. So just to be a bit more precise here, you could strictly follow the name convention of the standard library to make it like one-to-one compatible, but I like to keep my own convention. So what I want to add is a new function here, void append, and this append function here is going to get a pet manager, pet pointer, pet, or let's just call this one element here. So that's like the element that we want to append to the linked list. Now it's important how we do this. Well, in general, what we need to do is we need to kind of like append this to some certain point. And what I want to like to do is I want to use pointer to pointers here because it makes things a bit more simple. I'm going to have an element pointer pointer, which means it's a pointer to an element pointer, and this one is kind of like the position, kind of like the insertion position. Let's call this one a bit more precise here, insertion position. Now this is the insertion position, and by default I'm going to set this one to the my first pointer. So this is where we start. The insertion position starts at this one. If this one is null pointer, we're gonna insert here. But if this one is not null pointer, we need to go forward until we find the first element pointer that is null pointer. So how do we do this? Well, I'm gonna say while dereferenced insertion pointer. So now we are back at the normal pointer. In this case, it's currently the value that we have here. And as long as this one is not null pointer, so as long as the pointer that we are trying to insert onto is not a null pointer, on the first iteration, it's going to be that one, because that one, if we take a pointer to that one, dereference it, we have the m first, which is null pointer, so this one will like never go into the while block or inside the code inside of the while. However, if this one is not a null pointer, so this one is pointing to some other element, we need to make sure that we actually change our insertion pointer. So our insertion pointer should now be the next pointer of the m first. So this is going to be equal to our insertion pointer. We need to dereference that to actually get the pointer value. Now we need to follow the pointer and get access to the next one, but we don't want to get direct access to the next one. We want to redirect our insertion pointer to now point to the next pointer of the first element, or if you even would go further, like the first, second, and so on, which is in general like moving this element pointer along the list. And as soon as the value of the dereferenced insertion pointer, so either this m first or any of the following next pointers, as soon as there is one null pointer, so the first one that is null pointer, first pointer, or the last one of the chain of the next pointers. As soon as we found like one null pointer, we need to make sure to assign them. So what I want to say is dereferenced insertion pointer, no, not you, dereferenced insertion pointer, which allows us to modify this pointer, is equal to a new, now we are creating a new object of type element, and what we're going to add to the constructor is the actual data that we want to append here, which is the element itself. And this is how you append to a linked list. This is a bit hard. We're going to maybe explore this in the future a bit, but the general idea here that's happening again, pointer to m first. If m first is null pointer, set m first to a new element. If m first is not a null pointer, continue on following these elements. So take a look at the element, take a look at its next pointer. If its next pointer is null pointer, then is not null pointer, continue on until the first one is null pointer. And since we have a pointer to a pointer, we actually don't have the real value of the next pointer. It's not that this element is going to be null pointer. This element pointer is always going to be a pointer, so that we can later on change this pointer where it's pointing to a new element. This algorithm would be similar to another algorithm. I'm going to write this other algorithm here again, because this one is a bit better to understand and better to visualize what's going on. Really what we are doing is, if m first, else m first equals new element, and then we have an element pointer, element equals m first. Then we would say while element next. So as long as the next pointer is valid, element gleich element next, and then element next equals new element. However, I think that this code, no, not element, it's yeah, I renamed that one. That's not good. Element, let's call this one L element for list element. That's not a good idea that I've done, renamed them the same, but yeah, that would be the idea how you could do the algorithm as well. I personally think that one, even through the idea behind it, is easier, and you would rather find that implementation straightforward, but it is not good. It is not very clean, it's not very straightforward. This one is. This one is simple. Get a pointer to my start of the list, move this pointer to the pointer along all elements, always pointing to the next pointer, and as soon as the next pointer is no longer pointing to something, change the next pointer to be a pointer to a new element. That's really what's happening here. Now, as you can see, if I implement this append function, which is allocating objects with the new keyword, it's important that we destroy our memory itself, which is why we need a destructor of a linked list. So destructor linked list. And now inside of this destructor, we need to actually remove all elements from the list. Now, what I do here is not that straightforward, because yeah, maybe we want to do the straightforward implementation and see actually what's failing. So if you would be really curious, you would say like element equals m first, and you would do something like while element delete element, and say something like element equals element next. And if you see that syntax that I've used here, you would think that this would make a good for loop, which it might be, as long as it's an element. You could also check if this element is not null pointer, which I've done here as well, which I could remove down there as well, but not as far like that. You could remove this one down here, but I like to sometimes keep them in. Here, I like to not keep it in. I can't really say when I like to keep it in. I like to keep this in if you are dereferencing something. Yeah, I know, but yeah, let's remove this here as well to be at least a bit of have a bit of consistency in here. All right, so this is how you would think that the trivial destructor would look like, and you can already see that Visual Studio is actually quite smart and telling us that using uninitialized memory element, this is correct, because if you're deleting element, the memory gets uninitialized and you have no longer access to it, and this is bad. So you can't really do this one. If you would want to do this like that, you would have an element pointer next here, have the next pointer assigned before you delete this, and then on top here you would have next there and assign this to next. This would solve the issue. And since Visual Studio was smart enough to show this to you, I'm going to directly change this here. And yeah, this is how a really trivial linked list works. Now let's actually try out if this linked list works. Let's go to main.cpp and let's create a linked list LL. And then let's call append, and I want to append tabby, pointer to tabby, and pointer to Oscar. Maybe let's append a few more pointers so that you can just see how things work. And let's now make, we're going to step through that. Let's make a breakpoint here and hit F5 and actually see how our code works so that we can visualize how things go. All right, we start with that, and you can see that Oscar and tabby are properly initialized. Yeah, that's looking good. This is already working from last time. Now we can take a look at the linked list, and you can see that the first element in the linked list is a null pointer. So let's now with F, no, it's the wrong button. Haha, I wanted to press F11. Press F11 to actually go inside the append function and see what it does. So you can see that it starts with the element here. The element is actually a pointer to the cat. You can see this pet manager pet, which is actually a pet manager cat pointer. And you can see that the insert position is undefined. If I now continue on, you can see that the insert position gets pointed to a certain location, which is equal to the sys pointer, because the sys pointer is like the structure which is containing the data, and the first element and only element that is inside like this class is the next pointer, so, or the first pointer actually. So you can see that's the same, and you can see that's currently null. And what we can do is we can dereference it. If we dereference it, we check that value, and since this is never like anything else than null, you can see that we are skipping the whole main. And now you can see that we are dereferencing the insertion position and that we are creating a new element. If I hit F11, I'm going to go inside the elements constructor, which we really don't care. There it's initialized, and now as soon as we assign it, you can say that the insert position now has a proper value, and insert position now has a list element which has a storage pointer which points to the tabby. And it has a next pointer that points to null, exactly as it is desired. But you can also see, since the insertion position modified the first pointer, that inside of this, we actually have the same value here that is pointing to tabby, and the null next pointer for the first insertion. Now if we hit F11, we are going to go out of the linked list and back into our main, and now we're going to append Oscar. Now back again in this function, we are going to set the element pointer to the insert position. So the insert position now actually points to a pointer that has valid data in it and points to the tabby. So actually what you can see that we are now going inside of the while loop, and the while loop is inserting, or is putting the insertion position pointer to the next pointer of the current value of the insertion position, so actually to the next pointer of the first pointer, which you can see again the values have been changed here. The insert position is now no longer the same pointer than the first pointer, which is equal to the sys pointer. And you can see it has another value here, which is actually the value that is inside M first. So M first, you can actually see that it points to that certain value. And since the first element is the next pointer, the insertion position pointer is now the same than like the M first element. So it's pointing like to the first element inside of an element, which is currently null. And since this is now null, you can see that we're going to jump out of the while loop. And now we are actually going to assign the insertion position to a newly created element, which is again constructing ourselves an element. And if we are assigning this, you can see that now it has some proper values, which should point with the storage to Oscar, which is correct. And if we now take a look at the sys pointer, you can see that the first one points to here, tabby. And the next pointer points to a new element, which has in storage the Oscar. And which next is actually null because there's no more animals on here. So really what you have is you have like a cat and a dog and then a null, which is exactly how this is resembled. Now if I go back to my main file, let's just hop over a few more appends and take a look how it looks then. As you can see, now we have like a first, next, which at some point goes to a null, and we have like a dog, cat, or in reverse order cat, or actually the real order cat, dog. If you take a look at this, we have like here cat, dog, or here cat, dog, which is exactly what the linked list is now resembling. And that's all looking good. Now, as you can see, a linked list is quite useful. We can store data. However, currently our linked list can just append. And that's not what we want. We also want to access actually data. So let's find a way on how we can access the data. Well, what we like to write is we like to write a nice little add function. So what we want to get is a pet manager pet pointer, and the add function is going to take a size t index. And what I'm going to do here is I'm going to have an element pointer, and I'm going to call this one element, which is going to be equal to my first. And for size ti equals 0, I smaller index, I plus plus, I want to say element equals element next to actually seek that position, and at some point I want to return the pet at an element, which is basically returning the element storage if you want to get this. Very simple. We start at the first one, which is equal to an index of 0. If this is 0, the for loop is never fired and we directly return the storage. If the index is 1, which means the second pet, we're going to set it to the first one, going to go inside of the for loop, we're going to assign the element to the next one of the first one, which is going to be the second one, which is exactly what we want, and then we're going to return its storage. So that's all good and all nice and working quite fine. Now, if we would use that add, we could actually try this out. Let's try this out and say first pet, something like that. The first pet, it is ll at 0, and we could like dereference that to make this one print. And not print the pointer, because pointers are going to be printed. If we dereference it, we're going to have the reference here. We're going to also have like our second. Actually, let's number this through one pad. Let's make this like a list style. 1 pad, 2 pad. Let's make the breakpoint in here. Let's remove the breakpoint from there, and let's see what this code actually does. Oh, actually, went at the 2, which is not good. Actually, I want to go at 1. Let's rerun this. Let's make this a bit bigger, and you can see that we can actually access our pets in here. So first one is a cat Tabby, second one is a dog Oscar, and yeah, they have the age of 0 and they are living. That's nice. And you can see that our code actually works, but you can see that our code is bad because we need to hardcode it. We need to have a way to actually find out how many pets are in our linked list. How can we do this? Well, we're going to write a function size t count, which is going to get ourselves the count, and we could write this one like const no accept because this is easy. And now we would kind of like try to find out the count, and I would have like the count is by default 0, and then I have like an element pointer element equals my first, and while element I will do something like count plus plus, or I could even do this in a nice little for loop. So element equals first, element equals element next, and as long as we kind of like have an element, we're gonna increment the count. What is the problem here? While, yeah, this needs to be a 4. Exactly. And I'm just gonna increment the count, and then I'm gonna return the count to kind of like get the size. And what I could do then is I could write a nice little for loop for size ti equals 0, I equals ll count, or smaller ll count, ll plus plus, no, I plus plus, sorry. And then I could do my SCDC out, and I could write like my I plus 1 to have this like starting at 1 numeration dot, and then I would say something like ll at I dereferenced stdc out to print this one, and if I would write no c out, no endl, I'm an idiot. Yeah, like that. And if we would do this, we should get all the pads that are in here, which contains a hell of a lot of Oscar, but it's correct actually, because we have added the Oscar many times to the list. However, you might also recall that this one is not very efficient code. It's not a very efficient code because the linked list is traversed during counting. And you don't need to traverse it. Actually, what you can do is to accelerate this by wasting memory. So the idea in programming in general, especially in C++, is if you want to accelerate computation time, you're going to require memory. If you want to reduce memory, you need more computation time. That's always a trade-off. In this case, I want to reduce computation time, and I want to, for example, if you have like 1,000 elements in a linked list, this one is going to take 1,000 iterations, while we could accelerate this by just waiting 8 bytes of memory, and that's totally fine. So what I'm going to do is I'm going to actually get a count inside of here, size tm count, which is by default 0, and the idea is in general that we in here now just going to return our m count. That's changing that a lot, and the only thing that we really need to change is if we want to call append here, if we're going to add a new element, we just need to increment count. That's how simple we can accelerate this and make the computation way faster. It's not going to change anything on the behavior. The only thing that's really changing is the execution under the hood. This one is fast, and this count is really just accessing a member and not even calling a function if everything gets optimized away, which I personally then tend to like to prefix this with an inline to just make this a bit more clear that this one shall be inlined. And yeah, this gives us a nice things here. Now, normally you would start like implementing like operators for these, but before we're going to get to that, I do want to change a few things. First of all, we can only append here. We cannot remove it, but I also want to remove something. I want to erase, but what I do personally like to do is I like to erase at a certain index. Erasing is not something that I tend to do on the actual class itself. That's not what we want. We want to erase at an index. We're going to see later on why this is and how this comes together with finding elements and being consistent with that. But the general idea is you never want to erase like with an actual cat pointer. In this case, it's okay because it's actually pointers that we are using. And if we're using pointers, erasing with pointers would be good. Later on, if we would store like a real pet in it and not a pointer to a pet, we would not want to do this because if we would do this like that, we could have issues. The issue would be that we might have 2 pets with the same name, but like different kinds of pets. So what you really would do is you would want to find a way to properly find them and erase them then at positions. That's the idea. Right, so how do we erase at a position? Well, we need to seek the position, and then we need to remove that certain element. So again, what I'm going to do, I'm going to work with pointers to pointers because this is going to make this one a hell of a lot easier. And the pointer to pointer that we are tracking is it is going to be the element. We're gonna, I don't know how I want to call this one because I actually don't have the algorithm in my mind and I just need to come up with that while typing. But I'm just going to call this one element. We might change this one later. And we, in general, first start at the first element. Then we need to seek that. So size I equals 0, I smaller index. And then we would have like I++. So what we would do in here is we would do something like element equals element dereferenced element next pointer to that, and this would now allow us to seek. So if we are erasing at 0, it would leave us left with the first pointer. If we would seek at element of 1, it would resolve us with the first element's pointer to the to the second one, which is like the same one that we want to erase. So similar to that. How do we erase? Well, in general, you could like say we're just gonna delete the element, which wouldn't work because this is a pointer to a pointer, but what we would do is like we would delete the referenced element, which is exactly correct. This is how we could delete this. However, this is resolving us an issue. I'm going to show this issue to you. The issue is if we would now, after we printed that maybe, if I would now say ll erase the first element. If I would do this like that, and we would take a look at this, let's press a 5 and see what we got. No, we do need to do one more thing that I forgot because this is a pointer. We need to make sure that we set this to null pointer as well. So let's actually say the referenced element equals null pointer because this one is something that we can access. We just deleted the value, but the pointer to the pointer still exists and we can set this to null pointer. That's correct. And if we run this one, you can see that if we now take a look at the linked list, you can see that we have a hell of a lot of elements in there until we are at the end of the chain. But if I would now go and erase the first element, you can actually see that all of these get grayed out because they don't have a reference to there. I do still get a reference to that because we have had that one open up previously, but you can see that they are kind of like grayed out. They are still in here because I take a look at them previously, and Visual Studio is kind of smart and knows that we have made an issue here actually. And yeah, but what you can see is basically that the M first pointer is null pointer, which is wrong because we have really erased the first element, which means that this first pointer needs to be changed. However, the problem is that we do not have access to the other elements. That's bad. So really what we need to do is we need to take a look at the element before we delete this. So really the idea is that we kind of like store the next pointer. So we kind of like have the next one in here, and the next one is going to be equal to dereferenced element next, so that we have kind of like a knowledge of what the next pointer is going to be. Then we can delete the actual current element, and then we can set the previous value now to the next element that we had in the chain, which is going to be assigned properly. If the next one is null pointer, we're just going to assign a null pointer again, and the list would be empty. That's how it would work. But this one is going to also solve the problem that we might have an issue that we had here. So if we take a look at this now, you can see that the linked list is containing, again, a hell of a lot of data until we get to null pointer. And if I would now continue on, you can see that the linked list changed, and now you can actually see that it looks a bit different, but what you can really see is that the chain is still in here. You have like still like the first, next. So 1, 2, 3, 4 elements. Previously we had 5, which is still presented in here because we haven't changed the count, which I could do in here to be bad, but that's not really the point. And you could do this here, like taking the count and decrementing it here, which would make this one good as well. And you would now see that everything still looks good, and we just remove the first element. And if I would take a look at these, maybe let's quickly run this again and take a look at them. So the first one is, actually no, we don't want to take a look at them. We're just going to print them again so that you can see that we really erased the first element here. So let's do it like that. And it's going to print ourselves Tabby to Oscar, and after that just Oscar to Oscar, because we deleted the first element, which was the Tabby. We could delete the last one, which would be count -1, because count is 1 with 1 element, but we are 0 based indexed. So if we would do this like that, delete the last element out of it. Oops, that's not what I intended to do. We can see that even though this is now looking ugly again because I clicked around during printing, we have like Tabby to Oscar 5, and now we have Tabby to Oscar 4 because we removed one Oscar out of the chain. This is not removing like the elements itself, because the elements itself are just pointers and not actual animals. And yeah, this is now kind of like the idea here. Now, this code, even though we have added like the most fundamental functions like appending, erasing, counting, retrieving them, these are the most elemental things that we need. We can make them nice with pointers and have like copying and stuff like that. But that's really what we have done here, and what was nice. But the problem that we have here is now that we can just store pet pointers in here. And the idea would be to store like really anything in there, to have it able to manage all memory that we might want to manage in it. And the idea to manage all memory possible would be to make this templateable. Now, big issue here as well is that we need to store the cats separate from the list, but we might want to actually use the list to store the pets. And that's what we want to do now. We want to now make this a proper linked list, which can actually be can be done with a template. So let's actually change this to a template, type, not type def, type name t. So we're just going to call this one t, which is like the element type. And now we just need to change this. Now the storage is now no longer going to be a pet pointer. It's going to be a straightforward t, which is also what we're going to get in here. And we actually not just going to get a t here. We actually want to have 2 constructors that are going to be supported. A linked list normally supports 2 operations, copying something into the list or moving something into a list. So what we want to have is we want to be able to copy it, which would be a const t reference. And what we would also want to be able to is we want to move something, which is going to be a t reference for move semantics. And then I would do an std move here and move the data in there as well. std move, we got that one, and yeah, let's move it in here. So yeah, that's kind of like the basic idea on how to move something into storage here in an element. Now we just need to modify the list. This one, deletion of the list, we don't need it. It's all already templated, so that's all good. Let's scroll a bit through and see what's easy to modify. Let's maybe start with the T. Instead of actually getting now a T, we actually want to get a reference to the storage. So a reference to the element that's actually stored so that we are also able to delete it. Because if we would store a T pointer in here and we would just return T, we would just return the pointer, which would not allow us to modify the object that's in here because it's just a pointer. Having a reference there would mean that we have a reference to a pointer, which allows us to change the pointer, but also use it as a pointer. It's kind of like a pointer of a pointer, but a different syntax here. And you would wanna would have the same behavior than like a pointer to a pointer, but still the same syntax on how you would do this. You could normally assign a pointer to it because it's a reference, and the syntax would look fine there. Can show this to you in a second how this would work. All right, since we do like to have const correctness, I'm actually going to copy this whole add function again and make this one possible to access a const t reference for const modifier here, which would allow us to do it const again. There's one thing that I would maybe try to remove out of there. We might do a seek function that seeks a const element, because we do not, but no, I think it's actually good to have code duplication in here for a while. But just to make sure that you always have your const correctors in mind, this is how you would implement this one, so that you can also access a const list where you can't modify the reference but use it. This is still a const reference, not a const pointer, so the pointer is modifiable. Now arrays, it's everything good. There's nothing to actually consider here. Append is something that we need to consider. Now append, we need to have two versions of it, a const t reference element to append in there and a move append. Now how would we do that? We would have a t reference element and we would call std move in here. Now this again can be written easier. And this is actually something that we're going to write a bit easier, because when it is straightforward to do to remove code duplication, we want to do it. And in this case, it is straightforward because I'm going to have a private void append element, and this append element is going to get an element pointer element here, and this is going to append an element. This is straightforward onto how to append an element. Appending an element is basically that code here, but different, so I'm still going to leave it in here, but copy it over. The only difference that is going to be in here is that we don't insert a new element. We're going to insert the element that has been passed onto here. And what we're going to modify down there is we actually going to not do it like that. What we want to do is we actually want to have an element pointer element, or just going to call this one E, or actually we do not even need to put it in here. We can actually just call the append element function with the new in here. So really what we want to do is we just want to append element with the new element, which is going to make this one a hell of a lot of easier. And the same thing actually down there with that one. Append element, which is appending it in here with just the copy. So we have the copy here and the move down there, and we're both times appending an element, but with different parameters, and that's how things should go. Yeah, we could try to later on also modify that one, because what I would like to have is like a seek function, like seek element with an index, and then returning the storage. But this add is actually probably going to change in the future as well, and then we can modify it so that it's a bit less code duplication there. But this is something that would now change here, and this is what should make this already templatable. You can see that this linked list is no longer working, but if I would add a pad manager, pad pointer in here, this code should still work because we can add a pet pointer in there. It's not a problem to add a pet pointer as a temperature parameter. And since we changed everything, it should still be compatible and do the same thing that we've done previously. So 1 to 5 Oscar, 1 to 4 Oscar, still doing the same thing. But the really main change that we have here now is that we would now be able to actually store pets in the linked list. We actually do need, in this case, a pet pointer linked list. That's a bit bad that we need it actually, but there's actually no way around this. There's no way around that because we are storing the element actually in there. I do still want to have a few operators defined in linked list because they're going to be easy. I do want to have the operator, actually T reference operator array, size T index, which is going to be a inline operator, which is going to be a returning at index. And the same thing would go for const as well. So a const T reference const. There we have another const there, which should work as a charm, but this is a bit not syntax highlighted. That shouldn't be a problem, but we're gonna see in a second. This is just to make that one a bit nicer so that you can access this like an array, which is the general purpose idea here, that this one can be used like an array, right? That's the whole idea. And it shouldn't change anything. Okay, it does change something. What is the problem here? Okay, let's see. Inline const T reference. Okay, the const shouldn't be there. That's a good call. I don't know why I've added that there, but changing this would be, yeah, putting everything in here again, which should give us the same result, but it doesn't. Why do you not give me the same result? Okay, because I removed all the appends. Okay, that's good. So we have Tabby and Oscar, and then only Tabby, which is exactly what I wanted. Okay, so it still works. That's good. Okay, so this now gives us a linked list where we can store data in. We can really store anything in the linked list. We could create a linked list of integers, my ints. And you could write a for and I0, I smaller 1024, I plus plus, my ints append I would work, right? Would give us 1024 elements in the linked list, which would be kind of like wasteful there, or a bit, yeah, but it would be first, next, and this would really go on forever. And I think at some point Visual Studio is not going to be able to fit this on the screen. I don't know how it's actually then going to be looking. Like, yeah, it's just looking a bit bad. But yeah, in theory, you could have the data in here and you see all the integers and madness and stuff. And yeah, it's all dynamically memory allocated and madness is going on here. But yeah, that's the whole point of it. Madness is good. Or not. Nobody knows. Okay, but that concludes this video. Actually, no. Actually, I want to point you to some big issue that we have in our code, especially when we are getting too many elements. Well, as you can see, if we are writing a for loop like that and we are accessing it by the array operator, you're gonna see that every time we access the array operator, the add function is called, and the add function is always seeking. So in case we are seeking the 1024th element of a list, it's gonna have 1024 for loop iterations until we are arriving at the element. If you're writing a big for loop from 0 to count of elements, then you would, like, the first time you would seek, you would have 0 iterations to the for loop, the next time 1 iteration, and so on. So really the time it takes to access the array operator is increasing with I. So it's add is no longer an operation that is like, or add is not a good operation. Really, what we are doing with add and how we are iterating with a for loop, it's not a good idea, because it takes time, and this time is wasteful, because we could just store the element pointer and then always went to the next one, just to peek what we could do in the next video, and that's where we get to it, and where we get to what iterators are, and we're gonna have some nice stuff that's gonna be here. Alright, so thank you for watching. See you in the next video. Make sure to like and subscribe and have a nice day. Bye.